Hello, Math 135. This is Tracy. Welcome to Chapter 10, Hypothesis Testing with Two Samples. I think you're going to like this chapter because what we are going to have an opportunity to do now is practice all the stuff we did in Chapter 9, hypothesis testing. That's all this chapter is more hypothesis testing. Except now, instead of comparing a single population mean or proportion to some given predetermined number, we are going to be comparing two population means or two population proportions. Or in the case of matched or paired samples, the difference between results for a single population or matched pairs from different populations instead of two independent populations. So that's what our three sections are. 10.1, conducting hypothesis testing for two population means when the population standard deviations are unknown. We're going to skip 10.2 because that is comparing two population means where the population standard deviations are known, which is almost never the case. Although even if it were, it's really easy. It's just another button in the calculator. 10.3, we are going to conduct hypothesis testing comparing two independent population proportions. And in 10.4, we will be conducting hypothesis tests for matched or paired samples. We also have some text practice, so make sure you're practicing, not just doing the graded homework in Canvas. We are going to, in this chapter, figure out what kind of hypothesis test we are performing, make sure we can perform it by checking that the required conditions are met. If we don't meet the required conditions, we can't use the strategies we learn in this chapter, and we're not going to learn anything else. So we need to have samples and populations that meet certain conditions in order to do the testing we're going to learn how to do. We're going to figure out which calculator function to use, what to put into the calculator, how to use the calculator to find results, and then sketch and interpret. The types of hypothesis testing. If we have two independent population means that we are sampling, and our samples are independent, we are going to, in stats tests, conduct a two-sample t-test if the standard deviations are not known for the population, which is almost always the case. If the population standard deviations are known, we would, under stat tests, use the two-sample z-test, just like in Chapter 9. For a single population, if we knew the population standard deviation, we conducted a z-test. If we didn't know the population standard deviation, if we only had the sample, we conducted a t-test. If it is two independent samples and we are comparing population proportions, under stat tests, we would do the two-prop for proportion, the two-prop z-test. For proportions, we always conduct a z-test because for proportions, we always approximate that binomial distribution with a normal, so we do a z-test. And if we are going to either test a single population where we gather two measurements on each subject and find the difference, or we have two populations but we match our samples rather than finding independent samples, we are going to be conducting a matched pairs test of the difference between the two results. And we will use the same thing we did in Chapter 9 as if we had a single sample. Under stat tests, we will perform a t-test. Our conditions, if we want to compare two independent samples for their population means, we have two independent populations and we want to compare their means, we need to have two independent samples. The samples need to be simple, random samples, not biased in any way, shape, or form. And our samples either need to be large enough or the population itself needs to follow a normal distribution. Large enough is typically an N sample size greater than 30. Unless we have a really non-normal population, then we need an even bigger sample, but that usually doesn't happen. If we want to compare two population proportions, then we need two independent samples from our two populations. They need to be simple random samples. For each sample, the number of successes and failures needs to be at least 5. In each sample, we need at least 5 successes and 5 failures, or these techniques don't work. And depending on which book or video you're looking at, our sample can only be 1/10 or 1/20th the size of the population. If our samples are too big compared to the size of the population, then when we take our samples, we are changing the proportions of successes and failures that are left enough that our samples are no longer independent. Each individual subject in a sample has to have about the same probability of a success or a failure. If we take out too much of the population in our sample, then we don't have the same probability of success because we've changed the proportion depending on what our sample makeup is. So our sample can only be a tiny size of a tiny fraction, 1/10 or 1/20th of the entire population. Our matched pairs, again, we need simple random sampling. In these cases, we often have small sample sizes, but it doesn't change our requirement that if our sample sizes are small, the population they come from must be normal. Otherwise, we need those big samples again. In matched pairs testing, we are either taking two measurements from the same population, the same subject. So we would take a single subject, we would measure his blood pressure before medication, and then again after, and we would take the difference to find the change in blood pressure after using the medication. We would take the same subject and measure his blood pressure in his right arm and his left arm and subtract. And the difference would be the measurement for that subject. We would take the same subject and measure the results after one blood pressure medication, then administer a different blood pressure medication and measure the results after that and subtract the results. For that subject, the measurement would be the difference between the two results. We could also have two different populations, but we match the pairs of subjects. So we could have, for example, in a single election year, the height of the president and the height of the leading contender. So we have two different pools for our subjects, the president and the contender, but we match by election year. So we're not willy-nilly just gathering all the presidential heights and all of the contender heights and all that. We are matching each president to his contender and finding the difference, matched pairs. And then we will conduct a hypothesis test on the differences between the matched pairs of results. Again, we need to make sure that the population follows a normal distribution or the size is large enough. If we meet all of our conditions, then we can do the testing we will do in the next couple of presentations.